Просим прощения за задержку, мы сейчас уже начнем. Я хочу сказать вам, что эта лекция организована совместно Высшей школой урбанистики и компанией «Этом» при поддержке американского посольства. Перед вами Клаудио Сильва, профессор и преподаватель Нью-Йоркского университета. Он прочитает лекцию о больших данных и их применении в городском планировании и применении к параметрическому градостроительству. Claudio, you can start the lecture.
Oh, okay. It's probably easier to start. Can I use Thank you so much. First, I would like to thank all of you for being here. It's a great pleasure to be here and have the opportunity to talk to you about some of the work we're doing. I also want to thank Alexei and the other people, and Igor, that invited me here. It has been a wonderful visit. It's my first time in Moscow. Actually, it's my first time in Russia, so it's been really nice. So I'll talk about some of the work we're doing in data science for urban planning and for solving urban problems. As you're going to see, we're going to cover some pieces in different levels of detail. I want you to see if we can make this as interactive as possible. This is work with a lot of people, and I'm going to be mentioning some of the people and the at some point I'm going to show a slide with pictures from some of my collaborators, but I'm really representing here a huge number of people. So I want to tell you a little bit about the context that this work happened, and then I will move to more technical work. And I will, in a way, like some of the things I'm going to cover a little bit more at kind of like a 10,000 feet scale, and other things I can cover at a little bit more detail. It depends on what you guys want, actually. So a lot of this work has happened in the context of the Center for Urban Science and Progress. So what happens that Mayor Bloomberg, that was the previous mayor for New York, thought that after the 2008 financial crash, he thought that New York was too dependent on the financial industry. And so what he did was he started the center where the idea was to move more engineering into the city and applied sciences. So actually he put a bid out. Any university across the world could have responded to. And there have been multiple grants. One is to Cornell Tech, one is to NYU. There is another one to Columbia as well. And we were announced on April 23rd, 2012. And where CUSP sits is in this very interesting place right now. It sits between big cities. We all know that the world is urbanizing very, very quickly. We have about 50% of the people in the world live in cities, and in another 20 to 30 years, you're going to have about 70+% of the people living in cities. So cities are where a lot of the things happen. It's where a lot of the consumption happen, economic activities, innovation, but also cities are fairly complex to manage. So just think of things like trash, crime, all kinds of stuff like that. So the other thing is data. I mean, there's, probably everyone here has heard the term big data. I'll try to give a little explanation what it means if you're not familiar with it yet. But the idea is there's all this data coming along. So can we start doing data-driven decisions for cities? And that's kind of like where we live. So the idea for CUSP is, since we are in New York, can we use New York as a place to prototype solutions that then we can we can use in other places, right? So the idea here was not to actually be in a vacuum and just do work in New York for New York's sake, but really to do this one work there that we can reuse in other places. And I mean, as a Brazilian, actually, I definitely think that I want my work to be applied worldwide. In particular, it's very important to apply it in places like South America that are developing quite quickly. So what are we trying to do? Why this is hard? So one of the things here is that we have all this data, and we want to acquire data on everything about the city. And I'll show you some of the work we're doing, and I think you're starting to get the flavor of the work. Again, we're a very, very young research effort. So if things look a little bit simple, is because we're still kind of like at the starts of what I think is going to be a really nice revolution here. So we want to know everything about the infrastructure of a city, its roads, how they're operating, trains, everything there, right? We want to know about the environment, what happens when, how much it rains, how, what the level of pollution is. Noise, I didn't know actually how before I started working in this kind of problem, I had no idea that noise was such a major problem in cities, and it actually deeply affects people. And obviously we want to know also everything about the people, their economic activities, health, nutrition, their relationships, their opinions, everything there, right? And so one of the ideas here, if you think of the limit, is if you knew everything about a city, can you make it better, right? Can you use it to serve people better? That's kind of like what we're trying to do. And one of the things is we're kind of like lucky to be living in this time where a lot of the data is becoming available. So Mayo Bloomberg, another contribution that he did that is fundamental to the work we are doing, is that he did this New York City Open Data Initiative, where all the city agencies are opening up the data, and we are using some of this. And there are many efforts across the world, in France, in Brazil, everywhere on having access to open data. So let me tell you about what kind of things can you do with this data, right? So this is actually not work we did. This is work that was done at the University of Washington in Seattle. In a way, it's fairly straightforward work, but it's amazing the impact it had. So the idea here was to use crowdsourced data, so data from all of us as we use the buses, to know when the buses are supposed to be on an actual stop. If I was giving this talk in Switzerland, this would look really weird because, and I have no idea if the buses here follow the schedule, but in Switzerland they do, right? In the US they don't. So the buses are not, if the bus says that it's going to be there at 6:04, in the US it's not going to be there at 6:04. In Brazil, you don't even know if the bus is eventually going to get there, right? So what this thing did was really interesting because it then created, they created models for when the buses are going to be there in that region, and then it enabled people to know when they walk to the bus stop that the bus was going to be there. So one of the things that this had is that this increased the satisfaction of people. So there's a set of outcomes of this that I would have expected as a researcher that they got. Increased satisfaction with public transport, I think that I would have expected that. Decrease in actual waiting time, I would have expected that. But this one I didn't expect. So what actually happens is that about 78% of the riders reported increased walk. And the reason for this was that because they knew when the bus was going to be where, they felt pretty confident about walking to the next bus stop. Because if they were going to wait too long, they might as well walk. And so there is a huge public advantage when you do this because you're doing this walk and it's exercise for a lot of people. This is very significant. So another interesting success story was actually also done by Mayo Bloomberg. Michael Flowers that worked for him. One thing that happens in New York City because rents are so expensive is that we have this we have this phenomenon called illegal conversion. So I didn't know what this term meant. So, but here's what an illegal conversion is. It's when you have a use of a space for something that it was not planned to be used and it has not been authorized for use. To give you an example, let's say that you have an apartment that has one room and it was, and it has a capacity between 2 and 3 people to live in that apartment. But let's say that then 10 people or 6 people, whatever, decide to live in that apartment, right? So this can have major consequences, because imagine that you have lots of units, under which that is happening, and a fire breaks out in that apartment. I mean, it can be a major disaster. Lots of people can die. And actually, we've seen this in the news. I actually think that there's happening. I mean, one type of illegal use of any space. In Brazil, there was like a nightclub where a lot of people were dancing, and it was over capacity. It was being used way beyond its capacity, and a fire started, and lots of people died, because you were never supposed to have that number of people, right? So what they did, there's about 200 inspectors in the city to look at these incorrect use of space, and before they had a 13% hit rate. So when they went to a space and they were trying to figure out if the space was incorrectly used, a lot of times they would just use a hunch, like, oh, I think that space over there is not being used, it's not used incorrectly. And 13% is not that great, right? I mean, effectively basically means that you go to 10 places and only find one that is incorrect. So what the office of the mayor did is that they took a whole bunch of data sets. Just to give an example, they took late taxes, they took foreclosure proceedings, service cuts, ambulance visits, rodent infestation, right? And they correlate a lot of those with different locations in the city. And by doing that, they were able to increase the hit rate from 13 to 70%. So what this means is that obviously those places were, it's not like the place is totally illegal because the city was doing this. Is that those are places that people are using illegally that space, but you could never find it because you didn't have enough time to go through it. So you can see kind of like the use of data can kind of like really help to manage, right, the city. So these are some of this was work that wasn't done by us. This was done by people in the city. This was done by people at the University of Washington. So I want to show you some of the work we are doing, right? That is kind of like inspired by the same type of work. But one of the things we're trying to do is we're trying to push the technology forward, right? So we are trying to figure out what technology do we need to develop to enable people to do this kind of work more effective. So let's first describe a little bit what big data is. Feel free to interrupt me anytime. If I'm going too fast, I have a tendency to get to talk too fast. So data formats. So if you look at data, one of the messages I want to convey to you is that big data is not only about data being a large volume, right? So big data, probably the best way to think about big data is that it's data that is hard. Big data is big data for somebody if it's hard for you to manage. So for instance, the data format is complex. Let's say it's not all relational, because for relational databases we have really good ways to do this. Maybe the data is dynamic. So some data is batch, other data is streaming. There is data of all kinds of types, so the data is increasing at a fast rate for you. And then the other thing is maybe you just have, this is kind of like the obvious, is that you just have too much data, and that creates problems. So how do we make sense of this data? That's one of the, really the technology aspects from this is this whole area called the components of data science. So there's kind of like 3 main technologies that are used in almost all the big data projects. One of them is data management. Is how do you have data coming in, how do you store it, how do you query it, how do you save it, how do you handle it from coming and you massage it to be the right way. You have visualization interaction, how do you effectively take a look at the data, how you interact with it, how do you select the right components, and then kind of like machine learning and data mining, how do you automatically go to the data and pick up pieces that are going to help you to analyze it. All of these things that I talked about so far look very abstract. I'm going to make them very kind of like tangible by showing you examples, okay? Hopefully. So again, the context of this work, I told you about it. I said these are some of our collaborators. We have a group that does visualization, imaging, and data analysis at NYU. These are my colleagues and students and collaborators. We're about 40 people doing this. Most of the software we develop is actually available. So if you go to GitHub, you can get it there. And there are other places too. At NYU, not only we have this Center for Urban Science, but a lot of people, we also have a Center for Data Science, where really the focus of the center is just to study the principles and methods for extracting knowledge from data. They started actually at about the same time. So in a way, these efforts are very synergistic because in one center, we are trying to develop new techniques. In the other center, we're trying to apply them to cities. Okay. So now I want to go from the abstract, that's what we're doing, to the concrete. And the first example I want to show you is one where the idea here is what can we do if we have different data about the city. So, and how can we, in particular, we are going to be looking at an application that we've been working with architects. The idea here is actually that I'll show you two different applications from this. One of them is we are trying to quantify. If you look at a city, there's lots of different properties. So we want to find some way to actually study the different properties, in particular with the goal of being able to identify particular locations for development. So we are trying to figure out, how does this neighborhood look like? Let's say that I select this particular site for development. How does it change that neighborhood? How does it, what kinds of things it happens? So in the course of this, what we're going to do, and I'll go back and explain what this work after I show you a video. So I'll show a narrated video. I apologize that I neither speak any Russian or the video is also in English. I really apologize. If anyone has problems, I would be happy to show it again and to go slowly through this. I want to make sure that everyone gets this because it's kind of, I find it very kind of cool. Now, this is very fresh work. The paper was just accepted, so this is kind of like research that was just pretty much just. So let me show you the video. I think it's kind of self-explanatory.
Why do two neighborhoods feel similar or different? Why does a new building change the quality of the neighborhood and another doesn't? While the experience of the city is inherently subjective, the characteristics that shape the quality of it are not. To start to help answer those questions, we propose Urbane, a three-dimensional multi-resolution framework that enables a data-driven approach for decision-making in the design of new urban developments. Through a data-driven understanding of the existing and potential future city, architects, developers, and planners can better collaborate and make more informed decisions. The creation of Urbane posed several challenges. First was integrating 2D and 3D urban data sets from different sources and that don't share a format. Second was designing a system that could handle the sheer amount of 3D geometry that makes up a city. Next, to support urban scale spatial analysis, computation of measures such as view analysis and sky exposure have to be very fast to be integrated in the design and development process. Finally, creating a 3D interface that allows users to view and filter data sets and analysis at multiple scales. Urbane allows users...
Oops. Oh, sorry, I was annoyed that it's there. Sorry.
Format. Next, to support urban scale spatial analysis, computation of measures such as view analysis and sky exposure have to be very fast to be integrated in the design and development process. Finally, creating a 3D interface that allows users to view and filter data sets and analysis at multiple scales. Urbane allows users to seamlessly explore the city based on multiple 2D and 3D data layers. For example, noise, crime is visualized here, subway access. The data can be explored at different resolutions: the city, neighborhoods, and buildings. The opacity of the 3D buildings can be controlled for better visualization of the data layers. Urbane uses a parallel coordinate chart that allows for easy and intuitive filtering of urban data sets. Here we filter neighborhoods for various attributes such as subway access and noise. The bold blue line represents the average of all Midtown neighborhoods. The bold red line is the user-selected neighborhood, here the financial district. Filtering of various attributes allows users to understand the characteristics of Manhattan neighborhoods. For example, the financial district and Midtown are very similar across most attributes. At the neighborhood scale, the same filtering system is applied to individual buildings. Again, the blue line represents the Manhattan average. Here, we filter individual buildings for attributes such as built area, crime, and noise, identifying sites for potential development. Once specific sites have been identified, Urbane gives users the ability to replace existing buildings with new buildings, testing different tower sizes and program combinations for the maximum zoned floor area. The user can generate speculative buildings on many sites. Here we see a hotel with residential, an all-residential building, and an office with residential. Once buildings are generated, Urbane can compute derived 3D attributes from the data in buildings. This includes the view from buildings to selected landmarks, the impact of buildings on sky exposure to street level, and the impact of the buildings on the views of the existing context. This analysis can be used to evaluate the trade-offs between the value of the new development and its impact on the character of the neighborhood. This can facilitate the design and development process between architects, developers, and city planners.
Okay, so let's go through a few of those details there. So what we have is I'll describe to you some of the components of the system here. Actually, since I love this size of audience because we can actually, so let's say that we ran the application here. So we're looking, as you saw, we can look at the information in 2D, or we can look at it in 3D. So one of the things we can do here, this is a chart that we call a parallel coordinate. How many people know what a parallel coordinate is? How many people don't know what a parallel coordinate is? Okay, cool. So let me try to explain to you what this is. We have a number of a number of variables here. So imagine that what we are showing here is we have a list here of the different Manhattan neighborhoods. So, for instance, Battery Park City is an area of New York. Central Park is another one. Chelsea is another one. The East Village is another one, right? And so what we are doing, oops. I messed up. Let me just go back here. I messed up my demo. What happens that, do you guys see that for each one of these neighborhoods, I have some numbers. So I have the floor area ratio. I have crime. I have a score for food. I have a score for noise. I have a score for jobs, right? So jobs is obvious. It's kind of like the number of jobs in that neighborhood. People is the number of people that live in each one of them. Schools, I don't remember exactly what this is, but what the number is supposed to be here is kind of like a detailed, it's probably the number of students in that school district. Okay, so then what happens is, this is a big matrix of numbers. So what we are doing here is effectively, we scale, each one of these lines here goes from the minimum of this number to the maximum. And then what we do is that we mark a point here that is this number for every single one of those neighborhoods. And then what we do is actually connect them by lines. Right? So this has actually two purposes that are kind of interesting. One is, this makes it easy for me to look at data that is correlated, because I can basically look, let's say that I want to see if noise and the number of people go, are correlated. I put them next to each other, or maybe I want to look at price. I can do this. Okay. So basically, I can by effectively interacting with this, I can look at that whole matrix. I can look at that matrix in a compact way, right? But then the other thing I can do with this is I can do selection. So, and I will show you examples of this. So I can select. So let's say that I really care about public transportation. Let's say that I care about access to subways. I can select the neighborhoods that have a high score here, right? And let's say that I'm someone that wants to live in an area that has low crime. Then I would mark, somewhere that is low in this area, okay? Right, so that's basically what this thing is. So let's go back there to the presentation. Oops, my presentation is, sorry guys, let me find it. Somehow if the application is running it, I have to kill the application, I'm sorry. Okay. So, right, so it's clear what that thing is. So every time when I click at two different neighborhoods here, this is actually representing those two different neighborhoods. So I can compare them across those criteria that I cared about, right? So how can I use, so what kind of stuff can Urbane do for us? So one of the things it can do is we can look at different neighborhoods. So for instance here, we are marking the financial district. This plot, I can show you this interactively. So another thing that Urbane has is for each one of those layers, for the crime layer, the noise layer, the subway layer, all that comes actually from data from the open sources, you can look at that over the whole city. So for instance, if you look at access to subway, this is a map of that. So the financial district is the area that has the best access to subway. So you're always close to a subway in the financial district. Midtown, it's okay. You look here in the Upper East Side and you're out of luck, right? So there's only one line that goes to the Upper East Side. So effectively, we have these maps, so we can, and if you guys want, we can start here and then we can look at the crime map and we can, so this allows us to effectively look at the neighborhood and then, select the ones that we find are interesting. So, but one of the things, this you could do with Google Maps, okay? Right? But one thing that you couldn't do with Google Maps is the next one, is that what we're showing there is a layer, that is the sky exposure, right? So Urbane is able to actually intrinsically deal with 3D data. And that's actually one of the reasons that we kind of like built this, is that in a city, a lot of things that we want to do have to do with the fact that the city is not 2D, it's 3D. So sometimes, we need to deal with the geometry of the city. And Urbane does that for us. So just to highlight the capability to use these kinds of plots. So we come here and we select buildings. So instead of looking at neighborhoods now, we can, Urbane actually has information about all the individual buildings in New York. So we mark that are available in the Pluto data set. So we can mark and say, we want to look at buildings that are close to parks. So this is the park thing. And then the ones in green there are the ones close to park. Then we can say, I would like to, out of the ones close to park, I would like to mark the ones that are close to a subway, right? Okay? And then when I do this, see the ones in the middle here disappear, and only these stay because this is the West 4th subway entrance, and this here is the RQ subway entrance on the other side on Broadway. Okay, so effectively, this tool allows an urban planner or an architect, or actually just someone that is looking for a house, to effectively select different buildings for their use. Okay, so you can use this to do site selection for planning where to place buildings or when to modify neighborhoods. So since this was done with, we were working with architects for this, One of the features we also did was that we wanted to be able to literally add operations that would help an architect as when they would change a particular site. So let me show you one such operation. So here we are looking. The architect wanted to study what would happen if on the same site I put two different site types of buildings. So the building has to have effectively a constant area. So I can either make the building kind of like fatter and lower, or kind of skinnier and taller, right? So I'm trivializing I'll show you something later that is much more about designing the actual building. But what you see here is that the shorter building has a broader impact close to it in terms of the views, but it doesn't actually cast such a big shadow, while the taller building would modify the area of the neighborhood. The other thing is, this here is a depiction of what would happen to the sky exposure in the streets around the building. Okay, so actually cities like New York have sky exposure regulation. So you basically, there are some buildings that you cannot build because they might cover too much of the sun. Everyone on the same page with me, right? So we can run the application and play with this, but the idea here is to allow, instead of people having a hunch of where they want to build, this tool allows people to literally study the neighborhoods and compare them, and also compare different designs of buildings, right? So that's what I was telling you before, that by using the data, right, the data that we had, you can basically do something interesting with the city. So now, after you've decided on a particular location for your building, one of the things that you might want to do is, now you want to optimize for the type of building you have there, right? So we also explored this case study. So why don't I run this here for you?
One of the primary contributors in design of residential buildings is to maximize the view spread. Within real estate development, especially in New York City, better views can dramatically increase the value of a new building. However, in dense urban environments, desirable views are increasingly limited and challenging to detect without the use of aerial drone photography, which is limited in its application as it is taken from a single point rather than each window and is not quantifiable. In response to these challenges, we proposed a 3D framework that allows for the identification and exploration of building designs according to 4 different types of view analysis. This data-driven approach allows architects to quickly iterate building massing options with high view performance to meet client expectations. This is accomplished through a topology-based approach for design classification, which allows architects to consider a wide variety of building forms and work within practical workflow time constraints. The 3D analysis framework and catalog allows the user to pick from a range of geometric operations, such as extrude, loft, and fillet, for design optimization relative to view. It gives the users the ability to weight the relative value of 4 different view types of view analysis based on subjective preference. Lets the user explore high-performing options through filtering of metrics with the ability to save specific building forms for future comparison, allows the user to export selected forms with associated view data for development in other software, and finally allows the user to import building forms from other modeling software for view analysis and comparison with saved forms. We will next demonstrate the capacity of the framework through a typical architectural workflow. An architect first selects the spatial features that will be used to generate the parameter space, such as a lofted form with 3 massing blocks that can scale non-uniformly. Next, the user can weight the relative importance of the different view types into a combined view score, for example, 40% unobstructed, 40% landscape, 20% building variation. Unobstructed is the average distance from a window to obstructions within a human field of view. Landscape is the view to desirable landscapes such as rivers or parks. This analysis can reveal how certain landscapes are visible or not. For example, Battery Park, which intuitively might be assumed to be visible based on its proximity to the selected site, is not actually visible. Building variation measures the diversity in building age as a proxy for how varied the visual character of the buildings in the view are, as those typically correlate with the year built. In this example, the building variation analysis reveals unexpected diverse views low down in the building. Landmark is a view to selected landmarks such as the Empire State Building or the Brooklyn Bridge. Once these preferences are set, you can compute the design catalog. The design catalog is obtained by exploring the topology of the view function, which is the combined view score defined on the high-dimensional parameter space that represents the possible design variations. In particular, the set of maxima of the view function form the design variations that make up the catalog. By using this method of populating the catalog, the designer can explore and compare only distinct design variations, rather than large sets of extremely similar designs. The design catalog is explored by using parallel graph chart to filter for user criteria, such as specific view type, or floor plate efficiency, or the viability of each floor plate based on the ability to fit the elevator core. Once the user has isolated a set of designs they like, the designs can be saved for future comparison. Our 3D framework also allows for the filtering of specific windows within a single building. The perspective from any window can be shown, adding a qualitative evaluation aspect to the quantification of the view. Additionally, for the selected windows, the buildings that are visible can be highlighted. This can be used to isolate areas with view limitations or view opportunities that can inform future design refinement and the marketing of the building. The process of selecting spatial features and combined view score weighting can then be repeated to generate another set of high-performing building forms. These can be saved and compared against the previously saved designs. This allows the designer and their client to easily understand the view possibilities for the site relative to the design intent. Once one or two design massings have been selected, they can be exported as a mesh and a CSV file with associated view data for each window. The designer can then import the mesh and CSV file into a modeling software they're familiar with for calibration relative to other constraints, such as structure, environmental performance, program, and zoning. Once the design is elaborated, it can be imported back into our 3D framework, and the view performance can be compared against the previously saved options. Our 3D framework can perform computational view analysis for iterative design and seamlessly integrate into an architectural design workflow. It achieves this by reducing view analysis computation time, an intuitive user interface which facilitates comparative design exploration, and the ability to exchange geometry and window view data with other software platforms.
So basically, this is the idea here is kind of like the next step is to enable an architect to determine what that building should look like and where to place it in the massing in the parcel. One thing that is very useful is being able to look at, we have some way to globally quantify what the views are from the building, but you can even go to single apartments and single windows and look at what the view would be, and this can be very important for the architects, and that's kind of like the next generation of this is trying to actually do the actual pricing. We would like to actually do regression based on the fact that we can find built apartments that have similar views, right? And then we can, we would like to actually try to figure out how to do data-driven pricing, so we know what the pricing is, and we can apply regressions to that. Okay, so it's kind of like the introduction to static, data-driven, right? So one of the things that we would like to do is, this actually is the wrong, I think that this is the wrong presentation. At this point, the presentation was meant to be, let's see here. Oops, sorry, but up to that point it was the same, so 1 second here, guys, sorry. So I want to move now. What I was showing to you was a static data set. I want to move to a time-varying data set, so a data set that changes over time. Actually, I'm going to move to a much larger data set now. I wonder if people want to ask questions about what we just talked about before I move on. Yes.
I think, do you see the potential of this tool to kind of multiply their urban inequality? I mean, like, if everyone can find a place that's low in crime, with good views and so on, everyone would develop these places. And on the other side, places with high crime and so on would not receive any funding.
That's actually a great question. So I think that the issue, again, people are selecting. There's one variable here that people have to optimize. That is what they can afford. And so what my experience in New York is that anytime you get this area that has that great view, that those areas are things that usually we cannot afford. So I believe that I understand what you're saying, and it's actually a problem. So there is a process in New York called gentrification that is effectively people finding neighborhoods, as you're suggesting, that have the potential to be great neighborhoods, but are not yet. And then over the course of many, many years, buying whole neighborhoods and then redeveloping them later, right? And depending on how you do this, you can drive all the people all the poor people out from those neighborhoods, and it can devastate communities. The way that the city tries to deal with that, and actually there's a center at NYU called the NYU Furman Center that their main purpose is to study exactly these sites, to identify these sites and identify these processes, and to suggest to the city interventions that would mitigate, kind of like bad consequences for people that are not as well to do. So, I mean, personally, I'm only working on the technology. It's always my answer because I'm a computer scientist and a mathematician, so that's what I do. But I think that the policies, the issue of policies, is something that is orthogonal to this. And actually, I think that tools like this might be useful for policies even, because people can. This kind of tool is enabling us to do a kinds of analysis and regression in neighborhoods that we couldn't do otherwise before, right? Does this answer your question, kind of? I don't really have a good answer in a way. So, but that's a great question. Yes, please.
Hello. Is it also possible to add the information from standard like sensor networks about lighting, and also it's like an open framework?
Yes. So this is being developed, and the reason I showed two applications. Thank you so much for the question. I showed two applications of effectively the same technology is because it's really like a framework. So we are building all the building blocks from this, and we are using different applications. So another application that we are working on is actually modeling noise. So what happens in noise is that we can only directly measure noise in a few places in the city, but we would like to move those measurements to other parts of the city. And in order to do this, one of the things we're doing is that we are trying to use the physics, right? The fact that there are buildings and when they were built and all that stuff, and the knowledge that we got from one neighborhood into another. So these, all these sensing data, that's something that we're trying to add to the framework so we can handle those things. Cool.
Can your tool be used not for architectural design, but actually for urban design in terms of visual relationship? I mean, let's say we have a district that has to be built within a city with a view to the seaside, and we want to build towers, a lot of buildings, let's say. So each of them would have a good view to the seaside, so the price of the property would be as high as possible.
Yes, actually, that is one of the applications that the architects are working on care very much about, because it's so yes, you can do that in this with this tool. That's a great point there. Cool. So I want to give you a little bit of a flavor of kind of like, it's another dimension of the data here. So now we're going to be looking at data that changes over time. So it's more like the sensor data that you're talking about. But in some respects, it's going to be easier because it's going to be 2D data. But we're going to use that example for a few of the things we are doing that I think is going to, I'm trying to use this to illustrate to you guys some of the other work going on. So we're going to use taxi data now. So what happens is that in New York, all the cabs have GPS, and we actually have all the data, right? So here is data for 2011 and 2012. What I'm plotting there is all the taxi trips, or the volume of taxi trips in each day of the year over 2 years. So one of the things that is wonderful about the taxis is that you can think of them as really sensors of the city, right? So you get you can find events like, for instance, this was a hurricane, right? This was another hurricane. This is Thanksgiving, and if you see, you can also see the regularity of the what happens year after year. So you can see when summer is coming along, people go on vacation, right? It lowers. School starts. Look at that. There is a peak. Okay. You can even see small variations like here. This is that little variation is Valentine's Day, is when people are taking significant others to dinner on that particular day in February. I have to say that although I've been living in the U.S. for 25 years, a lot of these dates that happen there, I don't remember any of them because I don't get used to it. So I always wonder what that little thing was until actually I was being interviewed by a journalist, and I said, "Look, I have no idea what this is." And the journalist said, "Come on, it's Valentine's Day." So it's very interesting. So anyway, I'll show you how you can use. So we have this tool, and one of the main problems here is that it's a lot of data. So if there's 170 180 million trips a day. So one of the things is, and this data has a lot of different dimensions. You have spatial dimensions. You have where the cab picked up the person, where they left off. You have time dimensions, how long the trip took, what the physical length was, and also what the time length was. You have price information. You have how much the trip cost. You have tip information. How much tip people give, right? And actually, one of the things that is very interesting is that a lot of people want to use this data for a lot of different uses. For instance, some economists want to use this data to study people's behavior, right? So, for instance, I mean, unfortunately, there's some data we don't have. So if we knew what the race of the race and education of the driver versus the passenger, we could see how people react to people of different races by looking at their tip behavior, right? Because tip is a choice, right? Okay. Unfortunately, we don't have that data. We actually have that data for the driver, but we don't have that data for the passenger, right? The reason we don't have the data for the passenger is not that it doesn't exist, because actually in the data set, when the person paid with a credit card, it should be there. It's just that it's deducted from the data that we get. Actually, the city has that data. They get that credit card. If they actually were to merge that information with the one from the credit card company, we would be able to run this study in a way, right? So I'm just showing you that sometimes it's very interesting. You have a certain data set, and there are all these. Every time as a researcher, and I know a lot of you are, you can think of all kinds of really cool studies you can do with data like this, but sometimes we actually cannot physically do them, either because we don't have the other data sets, or it's impossible to get the other data sets that would go with it. But some of the, even if you just take this one data set, this is a very challenging data set, and you can do a lot of things that are interesting with this. So for instance, one of the things we're plotting here is It's just kind of like the time of the day that the length of the trip versus time of the day. We developed a whole tool to do this. I actually have the tool in my machine here. I could demo it, but the flavor is that the tool allows you to select different times, and it allows you to query the data, effectively allowing you to generate different kinds of analysis and do very simple data selection. So it makes it very easy to handle data like this. And you have to understand how hard it is to handle this data. So I will show you within the next slide. This data for many years is in the orders of hundreds of gigabytes to the low terabytes. So it takes an immense amount of time to do these queries if you don't have the right infrastructure to do this. And that's actually what the main computer science challenge was to building this tool. So just to give you an example, if you took 1 year's worth of data and you use SQLite, that is an open source database, it would take 52 hours to index this data set. Right? So this is several days. When we started trying to do this, we thought that the computer crashed. Right? So in our solution, this is actually our old solution. It can do the same thing in 8 minutes. But more important than the pre-processing time is actually the querying time. So when you want to query, so let's say you want to query about you take a complex query. What we call complex query is something that returns more than 100,000 elements. It would take a minute while I showed you this thing is working interactively, right? So we need to develop solutions if someone is actually going to use this that responds really quickly. All right, so we built this. There is a bunch of components that I really I'm going to skip. The one thing I wanna say that is kind of like very important for this is actually the querying and user interface component to this. So what happens is that let's say that you want to perform a query where you're selecting trips that picked up in a certain range, and there was a pickup location in Gramercy, there is a neighborhood of Manhattan, and then there was a drop-off in Times Square. This is you can see how complex these queries get. You have to write that in SQL. Using the system, it actually has a visual language for this. And you can actually write extremely complex queries in this visual language. And in our paper, we show that the two things are equivalent, and it's very easy to use. Okay, so here are some pictures. You can look at pickups versus drop-offs. This is like a week's worth of data here. We can look at things like all these needs here every day. That's 4 p.m. in New York. When they have the shift change. You have my favorite. You have like Saturday night in New York compared to a Monday night, right? So hopefully they show you that the cabs really reflect what people are doing, right? So on a Monday night, people still go to Lincoln Center, right? They kind of like still go to the Meatpacking District. But look at the East Village. It's mostly dead, and during a Saturday night, it's bustling with people. Okay. This is just for fun. This is just showing one cab, their behavior over 24 hours. You can see how much slower they are, like when they don't have a passenger. Look at that. And then when they have a passenger, they're much, much, much faster. Okay, so it's kind of cool. I guess that the person stopped, and then, yeah. So there's all kinds of stuff you can do with data like this that's pretty interesting. And if you notice, they keep going through the same kind of like roads the whole day, right? So this is also kind of interesting. Okay, so far I've shown you applications that are mostly using kind of like. I just showed you that a data management component. I showed you a visualization component of data science. I showed you the importance of the data management component. On the querying, I'm showing you the importance of interaction, but I haven't actually shown you anything in terms of automatically finding features. So what happens is that if you think about it, we have so much data, right, that you cannot really think that you can visually inspect every single data layer to find the features that you care about, right? Or to find interesting features on the data set, on this data set. So it's very important to have something that is automatic, it goes through all that data and picks up features for you, right? Potential features. So something that goes through your data, because it's so much data, picks up features, show it to you, and I would define a couple of things that I mean by feature. And then you would, the scientists actually would explore if that feature is relevant for them. So one of them is, one important feature is, let's say that you have lots of device traces, right? Is there a natural way to cluster them? So there is a technique that probably everyone here is familiar with called k-means, is when you have a set of points and you want to cluster points that are together. So for instance, like, I don't know, if I was applying k-means on this room here, maybe the three people in front, would be on the same cluster, and then, those people will be on the same cluster. But k-means is actually those that use R, there's just like a comment of k-means. So k-means set of xy points. It basically, what k-means does is that it basically takes, you give it a set of clusters, a number of clusters, and it just takes everything that is close to you, like it selects, k points to anchor the clusters, and then everything that is closest to those k points, it calls the same cluster, right? For those that haven't seen this, so how do you do this on trajectories? And we have a paper where we show how to do this. Effectively, what we do mathematically is that we define the metric to compare different trajectories in vector space, and then you can basically do the same thing so that you get what the expected behavior is. That is, if you have there we have 2,000 trajectories, 1,000 in each one of those two circles, and what our algorithm outputs would be this, right? Okay. So when you apply this to real data, so for instance, let's say that you have a bunch of, these are all the hurricanes in the 19th century. You apply this thing there, you get this, right? So it's nice now. It gives you see, like, it's separated. It naturally separated the hurricanes into clusters that they seem to be more coherent among themselves. So, but we're really interested in applications that are city-based applications. So I'll show you two of them. So one of them is, let's say that I have a lot of tracks of devices of actually people walking. And I'm not going to go through all the examples. You can look at the paper. This is a 2013 paper we had. But for instance, one thing that I thought was really cool is that our algorithm was able to find, for instance, the lunch spot, right? So it finds when this group of people go to lunch and then when they return from lunch, for instance. And it does that automatically. So the idea here is that we can go through all the data and then we can find all these features for you, and then we can show it to you, and then you can check if that is a relevant feature or not, right? Okay, so this is the whole idea of k-means. Is you apply k-means to a data set, you have a mental model what that thing is, and then you try to see if the clusters are actually relevant. And so we have a way to do that with trajectories. What is an extremely important set of data points, right? This is applying this to one of the really cool features of this particular technique is just how it handles noisy data. Because so here we have cell phone data, and we are looking for the different transportation modes in New Jersey, and we are able to do that. So I will show you really briefly another type of these automatic techniques. And I want to use this to actually emphasize a very important point when you're dealing with big data. A lot of us, when we are given a data set that is too large, the first thing we do is that we downsample that data set, and we then try to figure out if we try to find features in that downsampled data, and then we try to extrapolate those features to the full data set. Okay, so there's many ways that you can downsample a data set. You can do random selection of features, or you can do averaging, you can do aggregation of some type, right? But one of the things I want to point out to people is that it's extremely hard to do these operations in a way that doesn't actually add bias to your data or remove features. It would be as though I want to classify this whole, all of you by just looking at 3 people, let's say, because a lot of these data sets are so big that you need to take 1% or maybe even less than 1%, maybe a tenth of 1% of the data set in order to actually load that into a tool. Just to give you an example, the taxi data set, a spreadsheet of the taxi data set every day would be a spreadsheet with 500,000 rows. Okay, so even 1 day's worth of data would be a spreadsheet that is larger than you can meaningfully operate in Excel, right? So I would say that I mean, this is 1 day is already less. It's like 1/3%, right? Because there's 365 days on the year. So just to draw the point home here. So on May 1st in New York, actually the first Sunday of May, there is the bike tour. And during the bike tour, 6th Avenue goes empty for about 2 hours. And we are looking there for that event, right? So we can see here, 6th Avenue is empty from 8 to 9 a.m., okay? Let's say that we look at data where we are taking we take the whole data, the data for the whole day, okay? So this was May 1st. If we actually sort of look at that particular hour, we look at the whole day, we look at the day. Let's say that we look at May 8th, that is 1 week after, so this is the Sunday after May 1st, and we look at the Sunday before. When we look at these 3 days, that feature actually disappeared. Like you can even look at the number of trips too, and that feature effectively completely disappeared. It will be actually right here because it's such a negligible feature, right? But that's exactly what we would like to figure out is when that road was unblocked, right? So there's this major danger of anytime we do these subsamplings. And so developing techniques that work on the high resolution data is very important. And so I don't have time to describe this in detail. I have a paper on my website. We've been designing techniques that effectively go through data like this, goes through all the data, build indices, and then allow people to find what are events that happen on the high resolution data. Just to give an example here that we showed. So imagine this was the 5-borough bike tour. This would be that event there, right? When we query for this event with the technique that we developed, it would actually respond with other events of similar spatial characteristics and temporal characteristics. And in one of these events, if you were downsampling this data and looking for those events, you would lose it. Okay, so we've been working a lot on these automatic techniques that work on the high resolution data because this is very important. And the mathematics that we use for this is computational topology. It's a very well defined, very efficient, and very robust to noise set of techniques. So this is my last slide, real slide, is another thing that is extremely important is we're doing a lot of work on ways to grab urban data, not only from New York, but from cities around the world. We published a paper last year on that is shown here on your left, and all the code for that paper is on GitHub. It allows you to grab tens of thousands of data sets if you're interested, and then you can look at the paper. And one of the things we're working on now is it's very hard to actually find the data sets that you might want to use in your studies. And we've been working on what we call the urban data profiler. That is actually something that helps you to put data sets together so that you can build nice collections of data. So conclusions, we have this new center in New York. We're doing a lot of work in this area. We are working in effectively data science and data science for cities here. The results that I'm showing to you are relatively early results, meaning we've only been working on this for about 3 years. But I think it's already the research program here is becoming very exciting and very significant. And I think the best is yet to come. I'm really looking forward to interacting with you guys here and actually increase interactions with the research team here in Moscow, and hope that we can collaborate. So come and join us so VIDA is my research group, and CDS and CASP are the centers that we participate on. So thank you. Questions about the second part or about the first part, whatever. I'd be happy to take any questions.
Вопросы? Кому дать микрофон?
Did you have any actual collaboration with the authorities?
Yes.
Yeah, okay. I mean, like with programs of Michael Bloomberg, like Stop and Frisk, and this program Vision Zero.
So the Vision Zero, yes, actually. So the people in Vision Zero, the Department of Transportation is using the taxi tool that we developed in support of Vision Zero. The Taxi Limousine Commission is also using it. I'm on the Taxi Limousine Data Advisory Board. So I personally collaborate with people from DOT and TLC. Actually, it's funny you mentioned about the stop and frisk. So one of our students actually now is the head of analytics for the Department of Police, and he wants to use TaxiVis for visualizing the occurrences of police incidents. So yeah, again, one of the things is we interact with them. At least my role has been more on helping them with the technology, because I'm an expert in the technology. I'm not an expert on what, I'm not gonna be suggesting to them like, oh, you should move this from that, because I don't know much about about the actual use of transit laws, for instance, right? I don't know what's possible, what's legal, what's not illegal. So, but we are working with them closely. More questions? I wanted to get a sense of what you guys do. So, how many people are here economists? Students? How many of you are students? Okay, a few students. Professors? Okay, I think there's one here. Okay. So,
should I follow up with a question?
Yeah, I mean, go ahead.
So about the TaxiVis tool, you can tell by the look of it that it's custom built for this data set, but it probably can be modified for similar data sets and to perform similar analysis, which is why the colleague you were talking about was interested to use it for police analysis, for crime prevention, and so on, right?
Yeah. So actually, exactly. So the what is actually happening is that as we speak, there is a student that is finishing a public release of TaxiVis. That probably the most important thing is actually just to documenting all the data fields and making the data fields flexible. So instead of saying, so you have position that is kind of like starting and end, right? It's just position. So then you can query based on position instead of like something that says tip and price of the trip. It's any number that you can put there. And we actually hope to have this open source fairly soon. Because the important component of TaxiVis really, one of them is the querying piece, the visualization piece is another one, and then the indexing piece is probably one that is extremely important to people, because if you have a large data set, so let's say if you have a data set with a few tens of millions of data points, most other tools are going to break, and while TaxiVis is not. So we are preparing that for public release. But it's actually being used by the Department of Transportation.
I see. And what would you recommend? What would you recommend just to begin with for people who are really interested in the topic now? Where to start? Where to look for the tools? Where to look for the example data? It's really hard to come by a really large piece of data that's hard to manipulate in Excel, and that's meaningful, and that could be used to extract and to create new insights.
So I'm not sure I agree with that it's hard to find large data sets. Actually, for instance, the taxi data set, the New York City taxi data set is open, so you can download it right now. It's going to take a little while, but you can get it. If you cannot find it, I would be happy to send people a link to it. This paper here that I showed you, actually, let me do this way. So so if you look at this paper, what we did here, this is a very, very simple paper. We looked at a bunch of cities, and we looked at what we're plotting here is number of data sets available from this city versus population. New York is up there because it's the city that has the most data sets and has the largest population. So all these data sets here, there's a website on the paper that the code for this is available where you can use that code for downloading all the 9,000 data sets. So we started the 9,000 data sets.
Есть ли еще вопросы, Сережа?
Do you have any access to private enterprises datasets? Like I heard.
Yes.
Except
Yes.
Uber.
Yes.
Except
Yes.
Uber.
Yes, I do.
I heard a story about a retailer in Britain that was able to identify arrival of large quantities of people, like Polish, to Britain, and they actually, as far as I know, they made it public. So.
Oh, that's cool. Yeah, it would be wonderful if it's public. It would be wonderful to. Can you send me a link? I'll love to have a link. So, yeah, but we have access. So the private, certain private enterprises are releasing their data sets, but a number of private enterprises are not releasing their data sets. Hello. So I would love if all the data was public, right? So, or at least made publicly available, even if it's but we don't live in that world yet. I think one of the very important things that we should do as a community is to encourage people to develop platforms that we can crowdsource data, right? So, for instance, one of the things we badly need is better information about pedestrian traffic. And the best way to acquire that data would be to actually use data that we can all collectively generate. We don't need data on, for instance, like we don't need data that is personal. We just need enough, data from enough people that we would know, for instance, how full the streets are when masses of people are moving one way or another. So for instance, one of the issues I have right now is, for instance, I'm generating a bunch of that data for Apple and for Moves and for all these companies know exactly where I am, but they wouldn't share it with us researchers. So it would be really cool if we found some way to generate it ourselves. And the same way that that data for the buses was crowdsourced, we should crowdsource this data so that we can use it, right? So in a certain way, we should start taking a little bit more control over these data sets. And the same, like, how many people here know about OpenStreetMaps? Cool. So we should have more, OpenStreetMaps is actually an effort generated by the community. We should do the same for all kinds of other, like these other urban data sets, because I think that right now what happens is that the companies, many companies, as you're saying, actually have much more data on us than we have ourselves, and that is really very, very important if we're trying to do research on in cities. Cool.
So would you say that going open source would actually enable people to get more data about themselves and share it and analyze it? So for example, we have OpenStreetMap, and actually its coverage is much better in some parts of Russia than Yandex or Google's. And if, say, we had an alternative to Foursquare that would be open source and would release the data, would that be the way to go?
I think it is. So my personal opinion is that I believe that we should have our own apps that we have control over them. And actually, one of the things I'm trying to start is kind of like a whole suite of applications for handling urban data, and that are open source. People can go grab it, use it, contribute to it worldwide, because I think that that's very important along the lines of similar efforts. So you look at OpenStreetMaps, you look at, the major tools we use are open source. You take at R, LaTeX, right? I mean, there's so many cool tools, so we should build on that.
And perhaps if no one else has any more questions, I would ask a final question. Approximately how much of your work are you actually open sourcing? Is it 90%, 100%?
I can check the percentage, but we tend to open source almost all the work we do. Sometimes the reason that we don't just put it out there immediately. So one of the problems is that a lot of times you wanna do some code cleanup, or actually I don't think that people necessarily need to do this. But a lot of times, students that are working on their projects don't want to immediately put the code out there because they're still working on their thesis, and then they have, let's say, 2 other papers that they want to write, and they don't want anyone to scoop the next idea. That after they build like 90% of an infrastructure, but I actually try to encourage people to do this. At NYU, we actually, as part of the Center for Data Science, I lead the software working group, and we contribute to a lot of the major open source kits. Like, for instance, the scikit-learn, that is put the Python scikit-learn. One of the key developers in our team, the key developer of Julia, Stefan Karpinski, is just starting our team. So we are really trying to push the development of open tools that everyone can use. And I hope we develop more of those for urban. In particular, I think that one thing that we haven't done any work on, and if anyone wants to do this and wants to collaborate, it would be wonderful, is exactly developing crowdsourcing tools for getting data, right? So right now, all the data we are getting, we are kind of like dependent on other people to generate data, and I think that this is a mistake. I think we need to address the data issue, right? We need to find some ways to actually crowdsource our own data.
Okay. Thank you very much. Let's generate some applause.
Thank you. Thank you for hosting me here. It's been wonderful. It's been a wonderful week.
I was asking this question about